In March of this year, something extraordinary happened at 16.6 astronomical units from the Sun, the largest comet ever discovered. A frozen behemoth measuring 140 kilometers across began venting jets of carbon monoxide gas into the void of space. But here is what makes this discovery genuinely unsettling. When astronomers turned the Atacama millimeter ray back to observe the same comet, just 1 week later, the jets had completely changed orientation. The comet, it seems, is rewriting its own behavior in real time, and nobody can explain why. Before we dive deeper, if you find this kind of cosmic mystery as fascinating as I do, please hit that like button and subscribe to the channel. It tells the algorithm you want more of these deep dives into the latest space discoveries. And I am always curious. Tell me in the comments where you're listening from, what time it is there, and what you think could be causing these rapidly shifting jet patterns on a comet this far from the Sun. Now, let us explore what ALMA discovered. The observations, published in the Astrophysical Journal Letters in June, represent the first secured detection of molecular activity ever reported for Comet CU271, better known as Bernardinelli Bernstein. Nathan Roth and his team at American University and NASA Goddard Space Flight Center used ALMA to capture something that should not be possible at such extreme distances from our star. Carbon monoxide was erupting from discrete jets on the nuclear surface, rather than sublimating uniformly across the entire body. This comet sits more than halfway to Neptune, receiving barely a whisper of solar warmth. At 16.66 astronomical units, the temperature hovers around -348 F. Yet somehow, this ancient wanderer is explosively venting gas into space. On March 8th, LMAS observations revealed a pair of jets blasting from the comet's core. The spectrometry was unambiguous. Carbon monoxide, identified by its spectral signature at 230 GHz, dominated the composition. The team also detected the beginnings of a coma, that diffuse envelope of dust and gas that gives comets their characteristic fuzzy appearance. But when they observed again on March 17th, just 9 days later, everything had changed. The second observation showed only a single jet. The researchers suggest the other jet may have simply rotated out of view. Bernardinelli Bernstein is a rotating body after all, though its exact rotation period remains disputed. Some studies claim 20.6 days. Others find no significant periodicity at all. But here is where the mystery deepens. If rotation alone explained the changing jet patterns, we would expect predictable, cyclical variations. Instead, what we're seeing looks chaotic, dynamic. The coma that was clearly visible on March 8th had also vanished by the 17th. A coma does not just disappear in 9 days unless the outgassing driving it fundamentally changes. These are not the stable, predictable emissions we have come to expect from well-studied comets like Halley or Hale-Bopp. This is a comet that appears to be pulsing, erupting, quieting, and erupting again in patterns we cannot yet decode. Roth's team describes these observations as revealing explosive outgassing patterns that raise new questions about how this comet will evolve as it continues its journey toward the inner solar system. Previous observations from the Las Cumbres Observatory network captured outburst events, where Bernardinelli Bernstein ejected 10,000 to 100,000 tons of material within a single day. These are violent expulsions of ice and dust from a body that should be frozen solid. The ALMA observations confirm what earlier data hinted at. This comet has been active since at least 20 astronomical units from the Sun, based on dark energy survey images from 2017. Even the early TSS satellite observations from 2018, when Bernardini Bernstein was at 23.8 astronomical units, showed an extensive diffuse coma. This thing woke up in the coldest, darkest reaches of the outer solar system, and it has been getting progressively more active ever since. The thermal emission measurements allow the team to calculate not just the comet's size, but the amount of dust surrounding its core. Their values for nucleus diameter, approximately 140 kilometers, confirm Bernardinelli Bernstein as the largest Oort Cloud comet ever found. ALMA's extraordinary sensitivity made it possible to focus on an extremely faint thermal signal from an object so cold and distant that it should be essentially invisible. But detecting the size is one thing. Understanding the activity is another matter entirely. The standard models for cometry behavior simply do not account for what we are observing. The jet behavior, the rapid changes in orientation, the episodic outbursts, these suggest processes more complex than passive sublimation, driven by solar heating. Consider the nucleus itself. At 140 kilometers across, Bernardinelli Bernstein possesses significant gravity for a comet. Most comets are tiny, just a few kilometers in diameter, with gravitational fields so weak that ejected material escapes easily into space. But this monster has enough mass, estimated at 500 trillion tons, to gravitationally recapture some of its own ejector. Material blasted off the surface during an outburst might actually fall back down, redepositing on the nucleus in a cycle of ejection and recapture. This creates a feedback system, unlike anything in smaller comets. The surface composition changes as material falls back. Fresh ice gets buried under layers of dust. Pressure builds beneath newly formed crust until it ruptures in another violent outburst. The jets we are seeing might not be driven primarily by solar heating at all. They could be the result of subsurface pressure release pockets of volatile gas trapped beneath the surface finally breaking through weak points in the crust. The changing jet orientations observed between March 8th and March 17th might indicate that these weak points, these vents, are ephemeral. An outburst clears one vent, pressure redistributes beneath the surface, and a different location becomes the new release point. If this interpretation is correct, we're watching a comet that is not just sublimating, but actively restructuring its own surface geology in response to internal pressures we do not yet understand. And Bernardinelli Bernstein is still more than 5 years away from its perihelion in January 2031. The comet will reach its closest approach to the Sun at 10.97, just outside Saturn's orbit. If it is already showing this level of explosive behavior at 16.6 astronomical units, what happens as it gets closer? Will the outburst intensify? Will new jets form as different volatile ices reach their sublimation temperatures? These questions matter because Bernardinelli Bernstein is not just the largest Oort Cloud comet we have ever observed. It is possibly a pristine remnant from the earliest days of our solar system. Backward integration of its orbit suggests the comet had a previous perihelion of approximately 18 astronomical units about 3.5 million years ago. It has never penetrated deeper into the solar system than the orbit of Uranus in billions of years. Everything happening now might be the first time this ancient ice has felt significant solar warmth since the solar system formed. What we are witnessing is a time capsule opening. The composition, the behavior, the explosive activity, all of it offers clues to the conditions present when the planets were born. But those clues come wrapped in mysteries that challenge our fundamental understanding of how comets work. The rapidly evolving jets are just the beginning. Evolving jets, the comet that rewrites its own rules every week. The 9 days between Alma Esta observations in March reveals something profoundly disturbing about how we understand cometry physics. When Nathan Roth and his team looked at the data from March 8th and then compared it to March 17th, they were not just seeing a comet rotating to show different faces. They were witnessing active geological processes unfolding on a time scale that should be impossible for an object this cold, this distant, this ancient. Let us break down exactly what changed. On the first observation date, the distinct jets of carbon monoxide were visible, erupting from separate locations on the nucleus. The spectral data showed these were not diffuse emissions, but columnated streams, directed flows of gas accelerating away from specific vents. The jets had velocity components that varied between 0.38 kilometers per second and positive 0.021 kilometers per second. These numbers tell us the gas was moving in different directions, some material flowing toward us, some flowing away, indicating jets oriented at different angles relative to our line of sight. By March 17th, one of those jets had vanished from the observations. The remaining jet showed a different velocity profile, suggesting either a change in viewing geometry as the nucleus rotated or an actual change in the jet's behavior itself. Here is where the rotation hypothesis starts to break down. If we assume a rotation period of roughly 20 days, as some studies suggest, then 9 days represents nearly half a rotation. We should see dramatic changes in viewing angle, yes, but we should also see consistent behavior from the vents themselves. Instead, the coma that surrounded the comet on March 8th was completely gone by the 17th. A coma forms when outgassing from the nucleus creates a cloud of gas and dust around the comet. This material does not just vanish in 9 days, it expands outward at predictable velocities, gradually dispersing but remaining detectable for weeks or even months depending on the production rate. For the coma to disappear so quickly suggests the outgassing that created it simply stopped. The comet turned off. But why would a comet exhibiting such vigorous activity on March 8th suddenly quiet down by March 17th? One possibility involves the subsurface structure. Imagine pockets of carbon monoxide ice trapped beneath a layer of dust and refractory material. Solar heating, even at this extreme distance, warms the surface ever so slightly. Heat conducts downward, eventually reaching these volatile pockets. Pressure builds as the ice begins to sublimate in an enclosed space. Finally, the overlying cross fractures, releasing the built-up gas in a violent outburst. This model explains episodic activity. The comet erupts, vents the volatile pocket, and then goes quiet as pressure drops. The surface reseals, perhaps as ejected dust falls back and covers the vent. Pressure begins building again beneath a new weak point. The cycle repeats, but not necessarily in the same location. This would explain why the jets appear to shift position, why the coma comes and goes, why the entire behavior seems chaotic rather than smoothly periodic. The ALMA data provides crucial support for this interpretation. The fact that carbon monoxide was being released from discrete jets rather than uniformly across the nuclear surface tells us the sublimation is not just a surface phenomenon driven by direct solar heating. If it were, we would see relatively uniform alking from the entire day side of the nucleus. Instead, we see focused emissions from specific vents, exactly what we would expect if subsurface pockets were rupturing through weak points in the crust. Consider what this means for the comet's evolution. Every outburst restructures the surface. Material gets ejected, falls back, redistributes. The nucleus is not a static object slowly sublimating away. It is an active, dynamic world reshaping itself in response to internal pressures. The surface we see is constantly being renewed, buried, and exposed again in an ongoing cycle of violent geological activity. What if the changing jet behavior is not random at all, but follows patterns we simply have not recognized yet? Comets are not geologically dead. They have internal structure, possible layering from their formation, regions of different composition, and volatile content. As the nucleus rotates and different regions receive solar illumination, we might be seeing a complex interplay between multiple volatile species, each with its own sublimation temperature and behavior. Carbon monoxide is the molecule ALMA detected, but Bernstein almost certainly contains other volatiles. Ammonia and carbon dioxide have already been implicated in the comet's activity at greater distances. Nitrogen, methane, and other supervolatiles might exist in smaller quantities. Each of these species responds differently to solar heating. Each might dominate the outgassing at different times depending on local conditions, surface temperature, and subsurface structure. What we might be witnessing is a competition between different volatile reservoirs. One region rich in carbon monoxide erupts, creating the jets ALMA observed on March 8th. As that region depletes or recals, activity shifts to a different area with a different composition or a different depth of overlying material. The comet's behavior appears chaotic because we are seeing the superposition of multiple processes, operating on different time scales. This complexity becomes even more intriguing when we consider Bernstein's size. The nucleus has genuine gravity, enough to hold onto a significant fraction of its ejector. When material erupts from a vent, not all of it escapes. Some of it follows ballistic trajectories that bring it back down to the surface, potentially kill them away from where it originated. Over time, this process redistributes material across the nucleus, mixing surface and subsurface components, creating new layers, burying old ones. The feedback between outgassing and redeposition could create patterns that look almost biological in their complexity. A vent opens, ejects material. Some falls back and partially seals the vent. Pressure builds elsewhere. A new vent opens. The nucleus is playing a kind of geological whack-a-mole with itself. And we're only just beginning to understand the rules of the game. What makes the ALMA observations so valuable is their ability to see through this chaos and identify the molecular composition of the outgassing. As Bernstein continues its inward journey, ALMA and other observatories can track how the composition changes. Will water vapor start to appear as the comet gets closer and warmer? Will we see different molecules dominating the emissions at different heliocentric distances? The jets are not settling into a predictable pattern. They are evolving, changing, responding to processes we are only beginning to glimpse. As the comet continues inward, approaching its perihelion in 2031, the activity will almost certainly intensify. More volatiles will reach their sublimation temperatures. The outburst might become more frequent, more violent. The nucleus might even begin to fracture if the internal stresses become too great. The changing jets are not just a curiosity. They ray a window into the interior of a pristine solar system remnant, a comet that is revealing its secrets one explosive outburst at a time. And some researchers believe those secrets might be far stranger than anyone expected. Panspermia vindicated. Wickramange's controversial microbial theory. There's a theory about Bernardinelli Bernstein that mainstream astronomers prefer not to discuss in polite company. It comes from Chandra Wickramange, a controversial figure in astrobiology who has spent decades arguing that comets are not just frozen relics of the early solar system, but active carriers of life itself. According to Wickramange, the explosive outburst we are witnessing at 20 astronomical units from the Sun can only be explained by one thing: microbes. The panspermia hypothesis, the idea that life exists throughout the cosmos and travels between worlds on comets and asteroids, is not pseudoscience. It is a legitimate scientific hypothesis with a long history stretching back to the 19th century. What makes Wickramange's version controversial is not the basic concept, but the specific mechanisms he proposes and the extraordinary claims he makes about what we are. observing in comets like Bernardinelli Bernstein. Here is his argument. At 20 astronomical units from the Sun, the temperature of the comet's surface hovers around 60 Kelvin, minus 211 C. At this temperature, water is frozen solid as steel. Carbon dioxide and ammonia can sublime it, but the energy available from sunlight at this distance is minimal. The outburst observed on Bernardini Bernstein in September 2021, where the comet ejected tens of thousands of tons of material within a day, released far more energy than can be accounted for by simple solar heating and volatile sublimation. Wickramasia proposes instead that the comet's nucleus contains subsurface lakes of liquid water, kept warm not by the sun, but by radioactive decay of elements like potassium-40, uranium, and thorium within the nucleus itself. A body 140 kilometers across contains enough radioactive material to generate significant internal heat over billions of years. This heat creates pockets of liquid water beneath the icy surface, and in those pockets, according to Wickramasia, microbial life thrives. The metabolism of these microorganisms produces gases, primarily methane and carbon dioxide. These gases build up pressure beneath the ice crust. Eventually, the pressure exceeds the strength of the overlying material and the crust ruptures. The resulting outburst vents not just gas, but living microbes into space, creating the observed cometary activity. In this model, comets are not dead objects sublimating passively. They are living ecosystems erupting periodically as their microbial inhabitants reproduce and metabolize. This is an extraordinary claim. Wickramasia points to several lines of support. First, the spectroscopic signatures of cometary dust and gas show complex organic molecules, patterns that he argues match biological material better than any non-biological alternative. Second, samples collected from the stratosphere during cometary encounters have yielded structures that resemble bacterial cells, though whether these are truly extraterrestrial or terrestrial contamination remains hotly debated. Third, and most relevant to Bernardinelli Bernstein, is the pattern of outburst. Wickramasia argues that purely physical models cannot explain the episodic nature of cometary activity, the sudden violent eruptions, followed by quiescent periods. Biological processes, on the other hand, naturally produce this kind of cyclic behavior. Microbes reproduce, consume nutrients, produce gas. Pressure builds, erupts, the cycle repeats. The mainstream scientific community has largely rejected Wickramagia's specific claims. The criticisms are numerous. The organic molecules detected in comets can be explained by non-biological chemistry. Ultraviolet radiation acting on simple hydrocarbons can produce complex organic compounds without any biological intervention. The supposed bacterial cells from stratospheric samples are more likely terrestrial contamination or misidentified mineral structures, and the outburst behavior, while complex, can be modeled using purely physical processes involving subsurface volatile pockets and thermal cycling. But here is where the discussion gets interesting. The energy budget problem is real. Solar heating at 20 astronomical units is weak. Modeling the observed outburst using only solar energy and volatile sublimation requires making assumptions about the nuclear structure and composition that are difficult to verify. Radioactive heating, on the other hand, provides a steady, long-term energy source that scales with the volume of the nucleus. For a body as large as Bernardinelli Bernstein, internal heating from radioactivity is not speculative, it is inevitable. The question is whether radioactive heating is sufficient to maintain liquid water in the interior. The answer depends on the nucleus composition, particularly the concentration of radioactive elements and the thermal insulation provided by the overlying ice and dust. Calculations suggest that yes, for a body this large, subsurface liquid water is thermodynamically possible. If liquid water exists in the interior, then the next question becomes unavoidable. Could life exist in those hidden oceans? Life on Earth exists in environments that are far more hostile than a subsurface cometary ocean. Microbes thrive in Antarctic ice and deep-sea hydrothermal vents. In solid rock kiln beneath the surface, they survive radiation doses that would kill any complex organism. They persist in dormant states for millions of years and revive when conditions improve. The real question is how life would get there in the first place. Wickramasia argues that life is ubiquitous in the galaxy, present in interstellar dust clouds, spreading from star to star via comets and asteroids. Comets like Bernardinelli Bernstein spend most of their time in the Oort Cloud, that vast shell of icy bodies surrounding the solar system at distances up to 100,000 astronomical units. In the cloud, comets are exposed to interstellar space, to dust and gas flowing between the stars. If that interstellar material contains dormant microbes, they could be incorporated into cometary surfaces during close encounters. Once inside the comet, protected from radiation by layers of ice and warmed by radioactive decay, These microbes could potentially revive and establish populations in subsurface water pockets. Over billions of years, they would adapt to the unique environment, perhaps developing entirely novel metabolic pathways suited to the extreme cold and isolation. This scenario sounds like science fiction, but every component is at least physically plausible. We know microbes can survive in space. Experiments on the International Space Station have shown that certain bacteria can survive years of exposure to vacuum and radiation, when shielded by even thin layers of protective material. We know complex organic molecules exist in interstellar space. We have detected them spectroscopically and found them in meteorites. We know large icy bodies can maintain internal heat. Jupiter as moon Europa and Saturn as moon Enceladus both have subsurface oceans kept liquid by tidal heating and possibly radioactive decay. What we do not know is whether life actually exists in any of these environments. The jump from plausibility to actuality requires evidence, and so far that evidence remains elusive. Wikraminsky's spectroscopic analyses are interesting, but not conclusive. His stratospheric samples are contaminated by terrestrial biology and cannot be definitively traced to cometry sources. His arguments about outburst patterns are suggestive, but can be explained without invoking biology. Yet Bernardinelli Bernstein presents a unique opportunity to test these ideas. The comet is large enough and active enough to study in detail. As it approaches perihelion over the next several years, multiple observatories will track its evolution. If Wikraminsky is correct, we should see specific signatures. The outburst frequency might correlate with the comet's internal temperature and the metabolic rates of hypothetical microbes. The gas composition might show anomalies consistent with biological production, rather than purely chemical processes. The dust might contain structures or molecules that are difficult to explain without biology. Most astronomers remain skeptical, and rightly so. Extraordinary claims require extraordinary proof, but the conversation Wikraminsky has forced is valuable, regardless of whether his specific theory proves correct. We are being pushed to think more carefully about the limits of our models, about the energy sources available in large cometary nuclei, about the possibility of liquid water and complex chemistry in environments we once thought sterile. The microbial hypothesis may be wrong, but the questions it raises are exactly the right questions to ask. The gravity paradox, how galactic tides control a 500 trillion ton wanderer Bernardinelli Bernstein, is loosely bound to the sun. This simple statement contains a profound implication that most people miss. When we say an object is loosely bound, we mean its orbital energy is so close to zero that even small perturbations can significantly alter its trajectory. For Bernardinelli Bernstein, those perturbations come not from planets or passing asteroids, but from the gravitational tide of the Milky Way galaxy itself. The comet's orbit has a semi-major axis of approximately 20,000 astronomical units. Its helion, the farthest point from the sun, lies somewhere between 40,000 and 60,000 astronomical units, depending on which calculation you trust. At these distances, the sun's gravitational influence is barely stronger than the collective pull of every other star in the galaxy. Bernardinelli Bernstein spends most of its orbital period not in the sun's domain, but in a contested region where galactic gravity and solar gravity compete for dominance. This has extraordinary consequences. We can calculate the comet's current orbit with reasonable precision, because we have observations spanning more than a decade. We can predict where it will be in 2031 when it reaches perihelion. But if you ask an orbital dynamicist to tell you where Bernardinelli Bernstein was 10 million years ago, or where it will be 10 million years from now, they will give you a probability distribution, not a definite answer. The orbit is fundamentally chaotic on long-time scales. The chaos comes from the galactic tide. Imagine the Milky Way's gravitational field as a landscape, hills and valleys of potential energy. The sun sits in one valley, orbiting the galactic center along with hundreds of billions of other stars. But the galaxy is not a smooth, featureless disk. It has spiral arms, regions of higher stellar density where the gravitational potential is stronger. It has molecular clouds, concentrations of gas and dust massive enough to perturb passing objects. It has stellar clusters, tightly bound groups of stars whose collective gravity creates local distortions. In the galactic field, Bernardinelli Bernstein, at 40,000 O from the sun, feels all of this. As the sun orbits the galactic center, it carries its family of planets and comets through different regions of the galactic gravitational landscape. Sometimes the external tide squeezes the Oort cloud, compressing it slightly and nudging objects toward the inner solar system. Sometimes it stretches the cloud, pulling objects outward. These tidal oscillations happen on time scales of tens of millions of years, far too slow to observe directly, but powerful enough to reshape the entire population of distant comets. There is another factor. The sun is not alone in its orbit around the galaxy. Every star we see in the night sky is moving, some in roughly the same direction as the sun, others in completely different orbits. Occasionally, one of these stars passes close enough to the solar system that its gravity perturbs objects. In the Oort Cloud, close in this context means within a few light years, close enough that the star's gravitational field becomes significant. Compared to the sun has weakening pull at extreme distances. Stellar encounters are rare, but inevitable. Calculations suggest a star passes within 1 light year of the sun roughly every million years. Closer approaches, within half a light year, happen perhaps every 10 million years. These encounters can dramatically alter the orbits of Oort Cloud objects, kicking them into the inner solar system or ejecting them entirely into interstellar space. Bernardinelli Bernstein has survived billions of years of such encounters, its orbit shifting and evolving with each close stellar passage. Backward integration of the comet's orbit attempts to account for these effects. Astronomers use models of the galactic gravitational field and catalogs of nearby stars to reconstruct possible past trajectories. The results suggest Bernardini Bernstein had a previous perihelion about 3.5 million years ago, at approximately 18 astronomical units, somewhat farther from the sun than its upcoming closest approach. But this reconstruction comes with enormous uncertainties. Small changes in the initial conditions, slight variations in the stellar encounter history, different models of the galactic tide all produce different past orbits. The same uncertainty applies to future predictions. After Bernardinelli Bernstein passes perihelion in 2031, it will head back out toward the Oort Cloud. Its outbound semi-major axis is predicted to increase by about 40%, meaning it will recede even farther from the sun than it did on its inbound journey. But where exactly will it go? Which stellar encounters will it experience over the next million years? How will the galactic tide evolve as the sun continues its orbit through the spiral arms? We cannot say with certainty. This unpredictability is not a failure of our models. It is a fundamental property of the system. Bernardinelli Bernstein exists in a regime where three-body dynamics, galactic tides, and stellar perturbations all matter equally. The mathematics of such systems is notoriously difficult. Small uncertainties in the current state amplify exponentially, making long-term prediction impossible beyond statistical bounds. What we can say is that comets like Bernard and Bernstein are temporary visitors to the inner solar system. They spend brief intervals, astronomically speaking, swooping in close to the sun before retreating back to the darkness. Some will return millions of years later. Others will be ejected entirely, their orbits stretched by a stellar encounter until they escape the sun's gravity and become free-floating objects drifting through interstellar space. Still others will have their orbits shrunk, transforming them into short-period comets or even causing them to collide with the sun or a planet. This randomness is how the Oort Cloud maintains itself. Objects are constantly being lost, ejected into interstellar space or sent into sun-grazing orbits where they disintegrate. But the cloud is also being replenished, capturing the occasional interstellar interloper or having scattered objects from the inner solar system kicked outward by planetary encounters. The balance between loss and replenishment determines the total population of the Oort Cloud, estimated at trillions of objects. Bernardinelli Bernstein's loosely bound orbit means it is particularly vulnerable to these processes. A stellar encounter that would barely affect a planet could completely reshape this comet's future. The sun's gravity holds it now, but that hold is tenuous. The galaxy is always pulling, always offering alternative destinations. Think about what this means for the comet's history. Bernardinelli Bernstein has been making this journey for potentially billions of years, sweeping in from the Oort Cloud, rounding the sun, retreating outward. Each cycle takes millions of years. Each cycle exposes it to stellar encounters, galactic tides, random perturbations. The orbit we see today is just the latest iteration in a long series of variations. The orbit we'll measure after perihelion will be different again. And yet, through all this chaos, the comet survives. Its massive nucleus, 500 trillion tons of ice and rock, provides gravitational stability. Smaller objects might fragment under the tidal stresses of close stellar encounters. Bernardinelli Bernstein holds together, a monument to the durability of large icy bodies formed in the early solar system. The galactic tide that controls its orbit also preserves it. By keeping Bernard and I Bernstein far from the sun most of the time, the tide prevents the intense heating and outgassing that would otherwise erode the nucleus. The comet remains pristine, a frozen archive of conditions for billion years ago, precisely because it spent so little time in the warming inner solar system. We are witnessing one of its rare visits, a cosmic alignment that brings this giant within range of our instruments. The opportunity is fleeting on human time scales, but geologically instantaneous. In another few years, Bernardinelli Bernstein will begin its long retreat, and we will not see it again for millions of years. Unless, of course, the galaxy decides otherwise. Blacker than coal, the dark secret of the solar system's largest nucleus. Bernardinelli Bernstein absorbs 96% of the sunlight that reaches it. Let that sink in for a moment. This comet, this icy body from the frozen edges of the solar system, reflects only 4% of incident light. It is darker than asphalt. It is darker than coal. It is one of the blackest natural objects we have ever observed in space. This is wrong. This violates our intuition about what comets should look like. We picture comets as bright, pristine snowballs, dirty perhaps, but fundamentally icy and reflective. Freshly fallen snow has an albedo around 80 to 90%. Even old compacted snow reflects 50% or more. Water ice, the primary component of most cometary nuclei, is inherently reflective. So, how does a body made predominantly of ice become blacker than coal? The answer lies in what happens to a comet that has spent billions of years in deep space exposed to cosmic rays, ultraviolet radiation, and the slow chemistry of the interstellar medium. The surface we see on Bernardinelli Bernstein is not pristine ice. It is not even dirty ice. It is a radiation-prone crust, a matrix of complex organic molecules created by billions of years of irradiation mixed with silicate dust and refractory carbon compounds that resist sublimation even when the comet approaches the sun. This crust has a name in the scientific literature. It is called the lag deposit, but that term understates what is actually happening. When volatiles sublimate from the nucleus interior, they carry some dust with them, but not all dust gets carried away. The larger, heavier grains fall back under the comet's gravity or never get lifted in the first place. Over time, these grains accumulate on the surface, forming a layer that insulates the ice beneath and darkens the overall appearance. But there is more to it than simple dust accumulation. Cosmic rays, high-energy particles accelerated by supernova and other violent cosmic events, constantly bombard the comet. These particles penetrate the surface, breaking chemical bonds, creating free radicals, driving reactions that would never occur under normal conditions. Simple molecules like water, methane, and ammonia are broken apart and reassembled into increasingly complex structures. Over millions of years, this radiation chemistry transforms the surface into a terry, carbonic material that absorbs light efficiently across all wavelengths. The process is called space weathering, and we see its effects throughout the solar system. Asteroids that should be bright based on their composition are darkened by billions of years of radiation exposure. Meteorites that fall to Earth often have black infusion crust from their passage through the atmosphere. But beneath that crust, many show evidence of ancient space weathering from their time as asteroidal fragments. Bernardinelli Bernstein's extreme darkness suggests it has undergone particularly intense space weathering, likely because it has spent so much time in the Oort Cloud, where shielding from the solar wind and magnetic field is minimal. The darkness has consequences beyond mere appearance. A low albedo means the surface absorbs solar energy efficiently, even at 16 astronomical units from the sun, where sunlight is faint. The black surface heats up more than a bright surface would. This absorbed energy drives sublimation of subsurface ices, contributing to the cometary activity we observe. The very darkness that makes Bernardinelli Bernstein difficult to detect also makes it more active than a bright comet at the same distance would be. There is an interesting feedback loop here. Activity brings fresh material to the surface from the interior. This fresh material is initially brighter, less processed by radiation, but exposure to sunlight and cosmic rays quickly darkens it. The newly exposed material undergoes the same chemistry that created the dark crust in the first place, just on a much faster time scale because the sun provides concentrated UV radiation that accelerates the darkening process. So even as the comet sheds its old surface through sublimation and outburst, it continuously creates new dark material to replace what was lost. The extreme darkness also tells us something about the comet's composition. The organic material responsible for the low albedo is not just simple carbon. Spectroscopic observations suggest complex aromatic hydrocarbons, long-chain molecules, possibly even prebiotic compounds. These are the building blocks of chemistry that might, under the right conditions, lead to life. Whether they actually do is a separate question, but their presence indicates that comets like Bernardinelli Bernstein carry significant inventories of complex organic material. When we talk about comets delivering water and organic compounds to the early Earth, we're talking about material like this. The dark crust on Bernardinelli Bernstein is a sample of the ingredients that may have seeded life on our planet for billion years ago. Studying its composition, understanding the chemistry that produces such profound darkness, gives us insight into the raw materials available when life was getting started. But here is a puzzle. Bernardinelli Bernstein is not unique in its darkness. Many cometary nuclei show low albedos, typically between 4 and 6%. This consistency is strange. Comets come from different regions of the solar system, have different orbital histories, different sizes, different compositions, yet they all converge on similarly dark surfaces. Why? One possibility is that the surface darkening is a universal process driven by mechanisms that operate regardless of the comet's specific history. Radiation chemistry happens everywhere in space. Dust accumulation happens whenever a comet becomes active. These processes might naturally produce dark surfaces on any icy body given enough time and the right conditions. Another possibility is selection bias. We discover comets because they are active, because they outgrass and tails that make them visible. Inactive comets' bodies that have lost their volatiles or developed such thick insulating crusts that they no longer sublimate remain invisible to our surveys. We might be seeing only the subset of comets that have achieved a particular balance between activity and surface properties, a balance that happens to correspond to very low albedos. Bernardinelli Bernstein's darkness becomes even more intriguing when we consider its future. As the comet approaches perihelion, solar heating will intensify. More violent outbursts will expose fresh interior material. We might see the albedo change, brightening temporarily as pristine ice gets uncovered, then darkening again as radiation processing takes over. Monitoring these changes will tell us about the depth of the dark crust, the rate of surface renewal, and the efficiency of the darkening chemistry under different levels of solar irradiation. The darkness also affects how we interpret other observations. When we measure the brightness of the comet and calculate its size, we must account for how much light it reflects. A dark object appears fainter than a bright object of the same size at the same distance. Early estimates of Bernardinelli Bernstein's diameter were uncertain precisely because we did not know its albedo. Only after ALMA measured the thermal emission, which is independent of albedo, could we pin down the size accurately. The comet is 140 kilometers across precisely because it is so dark. A brighter comet with the same observed brightness would have to be much smaller. That darkness, that 4% albedo, is a signature. It tells a story of billions of years in the cosmic wilderness, of radiation bombardment and chemical transformation, of a surface continuously renewed yet continuously darkened by the relentless processes of space weathering. It is a story written in absorbed light, in photons that strike the nucleus and never return to tell us what they found. Perpendicular geometry. What it means when a giant cuts below the solar system. Bernardinelli Bernstein's orbit is inclined 95 to the ecliptic plane. In simpler terms, the comet is traveling nearly perpendicular to the planetary orbits. And right now, in late 2024, it sits directly below the inner solar system. This geometry is not just an interesting astronomical curiosity. It has profound implications for how the comet interacts with the solar wind, how it affects the local space environment, and what it might tell us about the structure of the Oort Cloud itself. Imagine the solar system as a flat disk with the sun at the center, and the planets tracing roughly circular paths around it. This disk, the ecliptic plane, defines the orientation of most objects in the solar system. Asteroids stay close to the plane. Most comets, even long-period ones, maintain orbits that do not deviate too far from ecliptic. But Bernardinelli Bernstein is different. Its orbit plunges down through the ecliptic, reaches a maximum southern excursion, then climbs back up, crossing the plane again years later. Currently, the comet is beneath the plane, moving through a region of space that few solar system objects ever visit. This position creates unique viewing geometry for observers. From Earth, we are looking down at the comet, seeing it from an angle that would be impossible if it were confined to the ecliptic. This geometry affects how we measure its properties, how we interpret its activity, and what features we can observe. The perpendicular orbit also means Bernardinelli Bernstein experiences the solar wind differently than planets do. The solar wind, that stream of charged particles flowing outward from the sun, is not uniform in all directions. It has structure, regions of fast and slow wind, coronal mass ejections, sector boundaries where the magnetic field polarity flips. Near the ecliptic plane, the solar wind is well steeped because that is where the planets are, where we send our spacecraft, where we have direct measurements. But above and below the ecliptic, particularly at high latitudes, the solar wind has different properties. It is faster, more uniform, less turbulent. The magnetic field configuration is different. The particle density is lower. Bernardinelli Bernstein, currently sitting at high southern latitude relative to the ecliptic, is being buffeted by a solar wind that is fundamentally different from what planets experience. This matters for the comet's activity. When solar wind particles interact with the coma, they ionize some of the gas and dust, creating a plasma. This plasma responds to the solar wind magnetic field, getting dragged along and forming the characteristic iron tail that points away from the sun. But the physics of this interaction depends on the properties of the solar wind. A faster, less dense wind produces different tail structures than a slower, denser wind. Observations of Bernardinelli Bernstein's tail. once it develops more prominently closer to perihelion, could provide rare insight into the high-latitude solar wind. We can treat the comet as a natural probe, a detector floating through a region of space that is difficult to reach with conventional spacecraft. The tail morphology, the ion composition, the magnetic field structure inferred from plasma observations all will tell us about conditions in this relatively unexplored region. The perpendicular geometry also affects how material shed by the comet distributes through the solar system. When a comet ejects dust and gas, that material does not just disappear. It becomes part of the interplanetary medium, contributing to the zodiacal dust cloud and eventually being swept up by planets or blown out of the solar system by radiation pressure. But the distribution of this material depends on the comet's orbit. A comet moving in the ecliptic plane spreads its debris along a path that planets are likely to encounter. This is how we get meteor showers, Earth passing through dusty trails left by periodic comets. But Bernardinelli Bernstein's perpendicular orbit means its debris is spread in a different direction, creating a component of the interplanetary dust cloud that is oriented vertically rather than horizontally. Over millions of years, as comets with randomly oriented orbits shed material, they build up a dust distribution that is roughly spherical rather than confined to a disk. Bernardinelli Bernstein is contributing to this spherical component right now. The dust it ejects today will orbit the sun for centuries or millennia before being destroyed by collisions or expelled by radiation pressure. During that time, it will reflect sunlight, creating faint contributions to phenomena like the Gaggen shine, that subtle brightening of the sky opposite the sun caused by backscattered light from interplanetary dust. The inclination of 95 is also a clue to the comet's origin and dynamical history. Objects that form in the protoplanetary disk generally have low inclinations because the disk itself is flat. High inclination orbits require some mechanism to tilt them, to pump energy into inclination at the expense of other orbital parameters. For Oort Cloud comets, that mechanism is typically stellar encounters and galactic tides operating over billions of years. Bernard and early Bernstein's nearly perpendicular orbit suggest it has been in this hot cloud for a very long time, long enough for random perturbations to scramble its original inclination into something completely uncorrelated with the ecliptic. This is consistent with the orbital integration, suggesting the comet has not been in the inner solar system for millions of years. It is a pristine Oort Cloud object, and its orbit carries the fingerprints of its long residence in that distant realm. When Bernardinelli Bernstein crosses the ecliptic plane in August 2033, it will pass through a region of space where the planet's gravitational fields are strongest. The crossing will not be close to any planet. The geometry does not allow for that, but it represents a moment where the perpendicular orbit intersects the plane of planetary motion. At that moment, the comet will briefly share the same geometric space as the planets, even though it is billions of kilometers away from the nearest one. The perpendicular geometry has one more implication. It makes Bernardinelli Bernstein visible from a wide range of latitudes on Earth. A comet confined to the ecliptic is only visible from certain parts of the planet at certain times, but a comet with high inclination can be observed from both northern and southern hemispheres at different points in its orbit. Currently, with the comet south of the ecliptic, southern hemisphere observers have the best view. But as it climbs back toward the plane and eventually crosses north, northern observers will get their turn. This global visibility is important for organizing observing campaigns. Amateur astronomers with modest telescopes can contribute to professional studies by monitoring the comet's brightness, tracking outbursts, documenting changes in the coma structure. The more observations we gather from diverse locations and viewing geometries, the better we can understand the three-dimensional structure of the comet's activity. The perpendicular orbit is not just a geometric oddity. It is a fundamental property that affects every aspect of how Bernardinelli Bernstein interacts with its environment, how we observe it, and what it can teach us about the solar system's edge. The fact that this giant comet cuts below the solar system right now at this moment in its multi-million-year orbit is a reminder that space is three-dimensional, that objects move in all directions, not just along the neat paths we draw on diagrams of the planetary orbits. Bernardinelli Bernstein is out of plane, out of pattern, and utterly fascinating precisely because of it. The self-capturing phenomenon, when a comet eats its own outburst, Bernardinelli Bernstein has enough gravity to capture its own ejector. This single fact changes everything about how we understand cometary evolution. Most comets are tiny, a few km across at most, with surface gravity so weak that anything ejected immediately escapes into space. But Bernard and Bernstein is not most comets. At 140 kilometers in diameter and 500 trillion tons of mass, it has a surface gravity approximately 110,000 of Earth's. That sounds negligible, but it is enough. It is enough to curve the trajectories of ejected particles, enough to bring some of them back down. enough to create a cycle of ejection and redeposition that has no analog in smaller cometary bodies. Think about what happens during an outburst. Pressure builds beneath the surface. The crust ruptures and gas vents violently into space, carrying dust and ice fragments with it. In a small comet, all of this material escapes. The nucleus loses mass permanently, slowly eroding away over repeated passages through the inner solar system. But in Bernardinelli Bernstein, the ejected material follows ballistic arcs. Some of it escapes, yes, particularly the smallest, fastest particles driven by the expanding gas. But the larger, slower particles, those do not have enough velocity to reach escape speed. They climb away from the nucleus, slow, stop, and fall back. The consequences are profound. Material that originated on one part of the nucleus lands somewhere else. A particle ejected from a vent near the equator might come down near the pole. Surface layers get mixed with subsurface layers. The geography of the nucleus is constantly being rearranged by this gravitational redistribution. This process has been observed on one other comet, Comet Hale-Bopp, which passed through the inner solar system in 1997, was large enough and active enough to show evidence of mass redistribution. Observations suggested that dust ejected from active regions fell back and accumulated in inactive regions, creating localized deposits that altered the albedo patterns on the nucleus. Bernardinelli Bernstein is even larger than Hale-Bopp, which means the self-capturing effect should be even more pronounced. The physics is straightforward, but the implications are subtle. Escape velocity from the nucleus is roughly 25 meters per second. Gas expanding from a sublimating vent can easily exceed this velocity, particularly close to the vent where the flow is concentrated and fast. But dust particles entrained in the gas move slower. They're dragged along by collisions with gas molecules, but they also have inertia and mass that resist acceleration. The larger the particle, the harder it is to accelerate it to escape velocity. Calculations suggest that particles larger than a few millimeter diameter cannot escape Bernardinelli Bernstein even if they are ejected from a violently outgassing vent. They simply do not reach the necessary velocity. These particles get lofted into temporary orbits around the nucleus, trajectories that intersect the surface somewhere downrange of the launch point. The time of flight might be hours or days depending on the ejection velocity and angle. But eventually gravity wins and the particles come home. Where they land matters. If material ejected from an active vent falls back onto that same vent, it could seal it, shutting down the outgassing temporarily until pressure builds enough to breach the seal again. This creates a self-regulating mechanism. Outbursts that are too vigorous choke themselves off by covering their own vents with fallback debris. Activity becomes episodic, pulsing on and off as vents seal and reopen. But if the ejected material lands somewhere else, it gradually builds up deposits in the inactive regions. Over time, the nucleus develops a heterogeneous surface with thick dust mantles in some areas and active ice exposures in others. This heterogeneity affects how the comet responds to solar heating. Thick dust layers insulate the ice beneath, preventing sublimation. Thin areas allow heat to penetrate, driving continued activity. The distribution of these regions evolves as material continues to be redistributed with each outburst. There is another effect. Falling material impacts the surface with non-trivial velocity. Even at a few meters, a chunk of ice or rock carries kinetic energy. Thousands of particles raining down across the surface deliver a cumulative impact that could fracture the crust, disturb the dust mantle, or even trigger secondary outgassing by exposing fresh ice. The nucleus is not just passively catching its own ejector, it is being bombarded by it, reshaped by it, evolved by it. The captured material also changes composition during its flight. Exposed to direct sunlight without the shielding of an atmosphere or surrounding coma, volatile ices can sublimate rapidly. A particle that starts as 50% water ice might lose most of that ice during its hours-long flight through space, landing as a desiccated remnant, enriched in refractory dust and depleted in volatiles. This differential processing creates chemical segregation. The most volatile materials escape entirely. Moderately volatile materials get depleted during flight. Only the most refractory components return intact. Over millions of years, this process concentrates refractory material on the surface while allowing volatiles to escape. The nucleus slowly accumulates a lag deposit, not just from material that never left, but from material that left and came back changed. The dark crust we observe might be partly the product of this cycling. Billions of years of material being launched, processed in flight, and redeposited in an altered state.
Bernardinelli Bernstein, self-capturing creates another possibility, one that sounds like science fiction, but is physically plausible. If the nucleus has regions of significantly different composition, material from one region could contaminate another through this redistribution. Imagine a pocket of complex organic material, perhaps synthesized by radiation chemistry deep in the nucleus, getting excavated by an outburst and scattered across the surface. Or imagine water ice from a pristine subsurface layer, getting mixed with ammonia-rich material from a different layer, creating chemical gradients that would not exist without the gravitational redistribution. This mixing has implications for spectroscopic observations. When we analyze the composition of the coma, we are seeing material that just sublimated from the surface. But that surface material might be a mixture from multiple depths and locations, homogenized by repeated cycles of ejection and redeposition. Untangling the original compositional structure of the nucleus requires understanding how this mixing process operates and accounting for it in our models. The self-capturing also affects how we interpret the comet's mass loss rate. Conventional models assume that material ejected from a comet is lost permanently. The production rates we measure for gas and dust are treated as upper limits on this nucleus erosion rate. But if a significant fraction of ejected material falls back, the actual mass loss is lower than the production rate suggests. Bernardinelli Bernstein might be shedding far less mass than its vigorous activity implies, because so much of what it ejects returns to the surface. This has implications for the comet's lifetime. How many more passages through the inner solar system can Bernardinelli Bernstein survive before it exhausts its volatile inventory? If self-capturing significantly reduces the net mass loss, the comet could remain active for far longer than a smaller body with comparable production rates. It might have a reservoir of volatiles deep enough to sustain activity for dozens or hundreds of future Protean passages, whereas a small comet might be spent after just a few. The self-capturing phenomenon transforms Bernardinelli Bernstein from a simple sublimating iceberg into a complex dynamical system with feedback loops, chemical processing, and surface evolution driven by its own gravity. It is eating its outbursts, recycling its debris, and in the process, creating a nucleus that is fundamentally different from the small comets that dominate our observational sample. Understanding this process is essential to understanding what Bernardinelli Bernstein truly is. 20,000 astronomical units, modeling an orbit that defies prediction. The orbit of Bernardinelli Bernstein extends to approximately 40,000 astronomical units at Ilion. To put that in perspective, Pluto orbits at an average distance of 39 astronomical units. Neptune, the most distant planet, sits at 30 astronomical units. Bernardini Bernstein, at Ilion, is 1,000 times farther from the Sun than Neptune. It is so far out that the concept of heliocentric distance almost loses meaning. At 40,000 astronomical units, the Sun is barely brighter than other stars. Its gravitational pull is a whisper competing with the collective gravity of the entire galaxy. Calculating this orbit requires integrating the equations of motion backward in time from the comet's current position. We know where Bernardi Bernstein is now with high precision. We have observations spanning from 2010 to 2024 enough to constrain its current trajectory accurately. Running those equations backward should tell us where the comet came from, what its Ilion distance was when it last passed through the inner solar system. But there is a problem. The orbit is extraordinarily sensitive to perturbations. Every time a star passes within a few light years of the solar system, its gravitational field tugs on objects in the Oort Cloud. Every time the Sun crosses through a spiral arm of the galaxy, the changing tidal field nudges cometary orbits. These perturbations are small compared to the Sun's gravity for planets and inner solar system objects. But for something at 40,000 astronomical units, where solar gravity is barely holding on, these perturbations matter enormously. The backward integration accounts for these effects as best it can. Astronomers use models of the galactic gravitational field based on observations of stellar motions and the distribution of matter. In the Milky Way, they incorporate catalogs of nearby stars, calculating which ones passed close to the solar system over the past few million years, based on current stellar positions and velocities. They add in the known physics of how orbits evolve under combined solar and galactic gravity. The result is not a single answer, but a range of possibilities. Bernstein's previous Elion likely fell somewhere between 35,000 and 45,000 O. The previous perihelion, about 3.5 million years ago, was probably around 18 astronomical units farther from the Sun than its upcoming close approach, but still well within the planetary region. The uncertainty comes from unknowns in the stellar encounter history and the exact structure of the galactic tide. These uncertainties do not just affect the past, they cascade into the future as well. After Bernardinelli Bernstein passes perihelion in 2031, it will head back out to the Oort Cloud. Calculations suggest its semi-major axis will increase by about 40%, meaning the next Elion could be around 60,000 astronomical units. But this is a prediction with wide error bars. A stellar encounter that we have not accounted for could change everything. A passing star could kick the comet into a shorter period orbit, transforming it into a more frequent visitor. Or it could eject the comet entirely, sending it into interstellar space, never to return. The galactic tide introduces another layer of complexity. The Milky Way is not a static structure. Spiral arms move. Molecular clouds form and dissipate. The overall distribution of mass evolves on timescales of tens of millions of years. The gravitational field that Bernardinelli Bernstein experiences today is slightly different from the field it will experience a million years from now. These changes are gradual, but cumulative enough to alter long-period orbits significantly over geological timescales. There is also the matter of a non-gravitational forces. Comets do not just respond to gravity. Outgassing creates thrust, a rocket effect that can change the orbit. For a small comet, this non-gravitational acceleration can be substantial enough to noticeably alter the orbital period over a single passage through the inner solar system. For Bernard and Bernstein, the effect is weaker because the mass is so large. 500 trillion tons is hard to push around, even with vigorous outgassing, but the effect is not zero. As the comet approaches perihelion and activity intensifies, jets of gas will create asymmetric forces on the nucleus. If the jets are oriented favorably, they could slightly increase the orbital energy, pushing the comet to a higher Elion. If oriented unfavorably, they could decrease the E energy, bringing future perihelions closer to the Sun. The magnitude of this effect depends on the total gas production and the geometry of the jets, both of which we cannot predict accurately because they depend on subsurface structure and volatile distribution that we cannot observe directly. The modeling challenge is compounded by the sheer timescale involved. Bernardinelli Bernstein's orbital period is measured in millions of years. One complete orbit from perihelion to aphelion and back again takes longer than the entire history of human civilization. We're observing an infinitesimal fraction of the comet's journey, a snapshot so brief that it captures almost none of the long-term orbital evolution. Extrapolating from this snapshot to predict the next million years requires making assumptions that may or may not hold. One assumption is that the stellar encounter rate remains roughly constant. Stars move through the galaxy, and the Sun's neighborhood changes over time. The density of stars in the local galactic environment fluctuates as the Sun passes through spiral arms and interarm regions. A period of high stellar density could produce more frequent encounters, perturbing Oort cloud orbits more vigorously. A period of low density could leave the cloud relatively undisturbed. We can model the average encounter rate, but the actual encounters are random events that cannot be predicted without knowing the future positions of every nearby star. Another assumption is that Bernardinelli Bernstein's nucleus remains intact. If the comet fragments during a future perihelion passage, the resulting pieces will have different orbits. Fragmentation is common in comets. Thermal stress, rotational instability, and violent outbursts can split a nucleus into multiple components. For a body as large as Bernardinelli Bernstein, fragmentation is less likely than for a small comet, but not impossible. If it happens, all our orbital predictions become moot.
Despite these uncertainties, the modeling is not futile. It gives us a statistical framework for understanding where Bernardinelli Bernstein came from and where it is going. We may not be able to predict the orbit precisely, but we can say that the comet is almost certainly an Oort Cloud object, that it has not visited the inner solar system frequently, that its future is tied to the random walk of stellar encounters and galactic tides. This statistical picture is valuable, even if the details remain fuzzy. The orbit also constrains the comet's thermal history. An object at 40,000 astronomical units is colder than anything in the inner solar system. The equilibrium temperature is just a few Kelvin above absolute zero. Cold enough that even supervolatile ices like nitrogen and methane can remain frozen for billions of years. The brief excursions to 20 astronomical units or closer during perihelion passages are thermal shocks, rapid heating events that drive activity but last only a small fraction of the orbital period. Most of the time, Bernardini Bernstein is frozen solid, inert, preserved in the deep freeze of the Oort Cloud. This thermal cycling has implications for the nuclear structure. Repeated heating and cooling can create stresses in the ice, fractures that propagate over time. The nucleus might be riddled with cracks, weak zones that make it susceptible to fragmentation, or that channel volatile outgassing in preferential directions. Understanding these effects requires knowing the orbit, knowing how often the comet has been heated, knowing the magnitude and duration of past perihelion passages. The orbit is the key to everything. It determines the comet's thermal history, its activity, its future fate. 40,000 astronomical units is not just a number. It is a distance that places Bernardini Bernstein at the boundary between the solar system and interstellar space, a wanderer between worlds, whose path is written in the gravitational ink of galaxies and stars. The primordial time capsule, never before this close in for billion years. Bernardinelli Bernstein has not been inside the orbit of Uranus in approximately 4 billion years. Let that time frame settle in your mind. 4 billion years ago, Earth was barely recognizable. Life existed only as single-celled organisms. The atmosphere contained no oxygen. The continents had not yet formed. The moon was closer. The days were shorter. The sun was dimmer. And Bernardinelli Bernstein was already out there in the Oort Cloud, a frozen time capsule slowly orbiting the sun at unimaginable distances. This is what makes the comet so valuable scientifically. It is not just large or active or unusual in its orbit. It is pristine. The material that makes up its nucleus has been locked in deep freeze since the solar system formed. While planets evolved, while asteroids collided and melted and differentiated, while inter-solar system comets sublimated away their volatiles over repeated perihelion passages, Bernardinelli Bernstein sat undisturbed in the darkness. The evidence for this pristine state comes from orbital dynamics. When astronomers integrate the comet's orbit backward in time, accounting for planetary perturbations, galactic tides, and stellar encounters, they find that the previous perihelion, about 3.5 million years ago, was approximately 18 astronomical units from the Sun. That is farther out than Uranus, which orbits at 19 astronomical units. Going back further, the uncertainties grow, but all reasonable models suggest the comet has not penetrated significantly deeper into the solar system for billions of years. This means Bernardini Bernstein's nucleus contains ice that has never been substantially warmed by the Sun. The interior temperatures have remained close to the equilibrium temperature at 40,000 astronomical units, just a few Kelvin above absolute zero. At these temperatures, chemical reactions essentially stop. Molecules are locked in whatever configuration they had when the ice first condensed from the solar nebula 4.6 billion years ago. This is primordial material, unchanged since the birth of the solar system. What can we learn from such material? Everything, potentially. The composition of the solar nebula, the cloud of gas and dust that collapsed to form the sun and planets, is written in the chemistry of pristine cometary ice. The isotopic ratios of hydrogen, carbon, nitrogen, and oxygen in Bernardinelli Bernstein's volatiles are fingerprints of the conditions in the nebula. Where heavy isotopes enriched or depleted compared to the sun? This tells us about mixing processes in the early solar system, about how material from the inner and outer nebula exchanged and homogenized. The organic molecules locked in the ice are equally informative. These molecules formed through reactions in the interstellar medium, before the solar system even existed, or through chemistry in the solar nebula itself. Analyzing their structure, their complexity, their chirality tells us about the prebiotic chemistry available when the planets were forming. Some of these molecules might be identical to the precursors of life on Earth. Others might represent chemical pathways that never got explored in the inner solar system, because conditions were too warm, too energetic, too disruptive. The mineral content of the dust mixed with the ice also holds clues. These grains condensed from the cooling solar nebula, or were inherited from the interstellar medium. Their composition reflects the elemental abundances and temperatures in different regions of the nebula. Refractory elements like calcium, aluminum, and titanium condensed first, forming minerals that survived even when volatiles sublimated. Analyzing these minerals tells us about temperature gradients, about where in the nebula Bernardinelli Bernstein's building blocks formed. But here is the challenge. We cannot sample Bernardinelli Bernstein directly. We cannot send a spacecraft to collect material and return it to Earth for laboratory analysis. The comet is too far away, too fast-moving, too recently discovered for any existing mission to intercept it. We are limited to remote sensing, to spectroscopy, to analyzing the light reflected and emitted by the nucleus and the gas and dust in the coma. Spectroscopy is powerful but limited. It can identify molecules based on their absorption and emission lines. It can measure isotopic ratios if the spectral resolution is high enough. But it cannot tell us about the physical structure of the ice, about how molecules are ranged relative to each other, about the detailed grain size distribution of the dust. Those details matter for understanding how the ice formed and how it has evolved. The best we can do is watch as the comet slowly warms, as subsurface layers get exposed through outbursts, as different volatile species begin to sublimate at different heliocentric distances. Each new molecule we detect, each change in the outgassing rate, each compositional shift as the comet approaches perihelion is a piece of data about the structure and composition of the nucleus interior. ALMA's detection of carbon monoxide is the first molecule definitively identified through direct spectroscopy. Previous observations infer the presence of carbon dioxide and ammonia based on the comet's activity at large distances and the brightness evolution. But these were indirect detections. Carbon monoxide is the first direct observation, the first unambiguous spectral identification. As Bernardinelli Bernstein continues inward, other molecules will appear. Water will become detectable once the comet gets close enough for water ice to sublimate efficiently. This should happen around 10 to 12 astronomical units from the Sun. Once water dominates the outgassing, we can measure its isotopic composition, particularly the deuterium to hydrogen ratio. This ratio varies between different solar system reservoirs and can tell us whether Bernardinelli Bernstein's water is similar to Earth as oceans or significantly different, which would have implications for theories about where Earth's water came from. Methane, if present, will appear at intermediate distances as its sublimation temperature is higher than carbon monoxide, but lower than water. Detecting methane and measuring its abundance relative to other molecules constrains models of the nebula chemistry. Methane requires specific temperature and pressure conditions to form efficiently, and its presence or absence tells us about the environment where Bernard and Nellie Bernstein accreted. Complex organic molecules, if they exist in sufficient abundance, might show up in the infrared spectrum as broad absorption features from carbon, hydrogen, nitrogen, and oxygen bonds. These features are harder to interpret than the sharp lines of simple molecules, but they provide information about the overall organic content and complexity. The nucleus is a library, and each molecule is a page. As the comet approaches the Sun, pages are torn out and scattered into space where we can read them. The problem is we cannot control which pages get read or in what order. The comet reveals its contents based on the physics of sublimation, not based on what we want to know. We are passive observers watching an ancient book slowly burn, catching glimpses of words and phrases, but never reading the whole text. Despite these limitations, Bernardinelli Bernstein offers a window into the early solar system that few other objects can provide. Short-period comets have been heated and processed by repeated close approaches to the Sun. Asteroids have been geologically active, melted by radioactive decay or collisions. Meteorites that fall to Earth are survivors, fragments of larger bodies that went through their own evolution. But Bernardinelli Bernstein is a survivor of a different kind. It survived by avoiding the chaos of the inner solar system, by staying cold, by remaining unchanged. Now it is coming in from the cold, and for the first time in 4 billion years, sunlight is warming ice that has never known heat. The molecules trapped in that ice, the dust grains frozen alongside them, the structure of the nucleus itself, all of it is about to be revealed. We're watching the opening of a time capsule, and we have no idea what messages from the ancient solar system we might find inside. 31 Countdown. Why this perihelion will rewrite cometry science. January the 23rd, 2031. Mark that date. On that day, Bernardinelli Bernstein will reach perihelion, its closest approach to the Sun at 10.97 astronomical units just outside Saturn's orbit. It will still be far beyond the traditional realm of cometry activity. It will never come close enough to be visible to the naked eye. But for planetary science, for cometry studies, for our understanding of the early solar system, that date represents a culmination of years of anticipation and preparation. We have 6 years to get ready. 6 years to build observing campaigns, to coordinate telescopes across the electromagnetic spectrum, to plan spacecraft observations if any existing mission can be redirected to catch a glimpse. 6 years to model the expected behavior, to predict which volatiles will dominate the outgassing, to estimate the brightness and activity level. 6 years to argue about what instruments should be pointed where and when. The scientific value of perihelion observations cannot be overstated. Every comet is different, but most of the comets we study intensively are small, a few km across with nuclei that fragment or fade after a few perihelion passages. We have studied Halley's Comet multiple times, but Halley is 75 years between visits and only 15 kilometers long. We studied Hale-Bopp in the 1990s, a large comet roughly 60 kilometers across, but it will not return for another 2,400 years. Bernardinelli Bernstein is twice the size of Hale-Bopp, and we are watching it during what might be its first perihelion passage in billions of years. The observations have already started. Ground-based telescopes have been tracking the comet since 2010. ALMA has detected carbon monoxide. The James Webb Space Telescope could potentially observe Bernardinelli Bernstein in the infrared, mapping the temperature distribution across the nucleus and searching for emission lines. From molecules to faint for ground-based detection, Hubble might image the nucleus and coma if the activity becomes prominent enough. Every major observatory on Earth and in space will likely take a look at some point. But the real science happens when we combine all these observations into a coherent picture. Spectroscopy for multiple wavelengths constrains the composition. Photometry tracks the brightness changes and outburst events. Imaging reveals the coma structure and tail morphology. Polarimetry tells us about dust grain properties. Radio observations measure the gas production rates. Each technique provides a different piece of the puzzle. What will perihelion look like? The comet is already active at 16 astronomical units. By the time it reaches 11 astronomical units, solar heating will be significantly stronger, about twice as intense. If the activity scales with solar irradiance, we should see roughly a doubling in outgassing rates. But the relationship might not be linear. New volatile species will start sublimating as temperature thresholds are crossed. Water ice, barely active at 16 astronomical units, will become a major contributor by 11 astronomical units. The character of the outgassing might shift from carbon monoxide dominated to water dominated. The coma will grow. Right now, it is barely visible, requiring long exposure stacking to detect. At perihelion, it could extend tens or even hundreds of thousands of km depending on the gas production rate and the solar wind conditions. A tail might develop, faint but detectable, pointing away from the sun as radiation pressure and solar wind push on the ionized gas and dust. The outburst, those violent eruptions that eject tens of thousands of tons of material in a day, will probably become more frequent as the comet warms. Thermal stress on the nucleus increases as temperature gradients steepen. Subsurface ice sublimating rapidly builds pressure faster. The crust fractures more easily. We might witness dozens of major outbursts in the months around perihelion, each one a miniature explosion that temporarily brightens the comet and alters the coma structure. There is a possibility, small but real, that the nucleus will fragment. Large comets sometimes split when thermal stress becomes too great. Comet Linear disintegrated spectacularly in 2000. Comet Schwarzmann-Wachmann 3 broke into dozens of pieces during its perihelion passage in 2006. Bernardinelli Bernstein is larger and probably more structurally robust, but it is also experiencing thermal stresses it has not felt in billions of years. If fractures propagate deep into the nucleus, if weak zones fail under the strain, we could witness the breakup of the largest comet ever observed. Fragmentation would be scientifically spectacular. Each fragment would expose fresh interior material. The composition revealed would tell us about layering in the nucleus, about how the ice and dust are distributed from surface to core. The fragments would have different orbits, slightly diverging as they move away from perihelion. Tracking those orbits would constrain the forces that split them apart and the mass distribution within the original nucleus. But even if Bernardinelli Bernstein remains intact, perihelion will test every model of cometary physics we have. The size, the activity, the composition, the outburst behavior, none of it fits neatly into the boxes we have built from studying smaller, more frequently observed comets. This is a new category of object, and the data we collect at perihelion will define that category for decades to come. The observations will also address fundamental questions about the Oort Cloud. How common are objects this large? Bernardinelli Bernstein was discovered by luck, noticed in archival images because it was bright enough to stand out at extreme distances. But for everyone we detect, how many are out there to faint or too far away to see? Statistical models of the Oort Cloud population depend critically on knowing the size distribution of its members. Is Bernardinelli Bernstein an outlier, a rare giant in a cloud dominated by smaller objects? Or is it representative of a whole class of mega-comets waiting to be discovered? The Vera C. Rubin Observatory, currently being commissioned in Chile, will help answer these questions. Once it begins regular operations, it will survey the entire southern sky every few nights, detecting faint, slowly moving objects that previous surveys missed. Predictions suggest Rubin could find hundreds of large Oort Cloud comets over the next decade. Each discovery will refine our understanding of the cloud structure and composition. But Bernardinelli Bernstein will remain special because it was first. Because we are watching it during its potentially first intersolar system passage in billions of years. Because it is the benchmark against which all future discoveries will be measured. The countdown to 2031 is also a countdown to understanding. Every observation between now and then builds our knowledge base. Every outburst teaches us something about subsurface structure. Every spectroscopic detection adds to the inventory of molecules in the nucleus. By the time we reach perihelion, we will have a comprehensive Perperian data set, a baseline against which to measure the changes that occur as the comet experiences maximum solar heating. Then, after perihelion, we watch it recede. The activity will decline as the comet moves outward and cools. The coma will shrink. The outbursts will become less frequent. Eventually, Bernardini Bernstein will fade from view, retreating into the darkness of the outer solar system. But we will keep tracking it as long as we can, measuring how quickly it fades, how its orbit evolves, whether non-gravitational forces from outgassing have measurably changed its trajectory. And then it will be gone, falling silent again as it climbs back toward the Oort Cloud. We will not see it return. The next perihelion passage is millions of years away, long after human civilization as we know it has ended or evolved into something unrecognizable. This is our one chance. 6 years from now, we witness something that happens once every few million years, the awakening of a giant. The science we do in those crucial months around perihelion will echo through astronomy for generations. Bernardinelli Bernstein is not just a comet. It is a gift, a visitor from the deep past carrying messages about the birth of worlds.